engine, which is used inside of the Google Chrome browser. My name is Mads Ayer. I'm a software engineer working at Google, and I'm working in Denmark in the office that's in a city called Aarhus. And in Aarhus, we've been building V8, which is the JavaScript engine used in Google Chrome. So in this talk, I'm going to tell you first something about Chrome. So why did Google want to build a new browser? And I'll tell you something about the features of Chrome. And then I'm going to dive a bit deeper into the JavaScript side and tell you something about the JavaScript engine and tell you some of the tricks that we did to make JavaScript execution really fast. Okay, so why did Google want to build a new browser? Well, the internet has evolved a lot over the last 10 years. So to illustrate that, here's a slide showing you the evolution of the internet. So this is the BBC webpage from July 1998 to August 2008. And as you can see, it's changed a lot. So in 1998, the page was basically just text with a few images. And now, in 2008, it's got lots of images, lots of video, lots of interactive content. And that's basically true of the entire internet. That is really evolved, and you've got much more interactive content on the web now. Also, users spend much more of their time inside of their browsers. We at Google spend a lot of our time inside of the browser. So when I'm not actually writing code as a software engineer, but when I'm doing my email or working with my calendar or collaborating on documents, all of those things happen inside of my browser. So instead of having these text pages of the early days of the internet, we now have full-featured applications running inside of our browsers. And in the same browser, in multiple tabs, we might have several applications like email, calendar, documents. So the browser is really this platform for applications. So the interesting thing is that the internet has evolved a lot, and web pages have gone from text to being these full-featured applications, but the underlying browser technology has actually not evolved that much. It's true that now we have tabs, and we have search boxes and stuff like that, but the basic architecture is still the same. So that's why Google wanted to build Google Chrome, a new browser. We wanted to try to push the evolution of web browsers to make them better platforms for web applications. And with Google Chrome, we focused on three things. We focused on stability, intuitiveness, and speed. So let me take each of them in turn. So for stability, Google Chrome uses a sophisticated multi-process architecture. And what that means is that if you have multiple applications running in multiple tabs, so say I'm writing something into a text field on a web page, and then I want to search for some information. So I open up a new tab, I navigate to a new site, and then something goes wrong on that site. So maybe the renderer crashes, or maybe the website hangs. Then in most current browsers, that means that your entire browser hangs. So the text box that I was editing, I can't get back to that, and I lose my work, so I have to redo it. That's not the case with Google Chrome, because in Google Chrome, each tab has its own process, which means that the content of different tabs is completely separate. So if I have my text box that I'm typing something into in one tab, I open a new tab, go somewhere, and something goes bad. Only the new tab goes bad. I can still navigate back to my old tab and continue working. So that gives you a much more stable browsing experience. And this is something that we feel are needed for web applications. If you have full-featured applications inside of your browser, like your email, your calendar, and your documents, just because there's something that goes wrong on a completely unrelated page, you don't want your email application to go down. So, so that's the stability. And we even do this for plugins as well. So if you have a page that uses a plugin, like YouTube uses Flash, I guess, to play videos. If Flash does something bad and Flash crashes, that's not going to kill your YouTube page, because Flash is running in a separate process. That's only going to kill the Flash process. and all the content that is drawn by Flash, but everything else on that web page will still be working. Okay, so that's for the stability part. We also wanted to make Google Chrome easy to use. So we wanted to basically make Google Chrome an invisible browser. We wanted people to be able to focus on the content and not so much on the browser. So Google Chrome doesn't take up much space on the screen. So it gets out of your way, basically, lets you focus on the content. Also, we've got flexible tab management. You can arrange your tabs any way you want. You can even drag a tab out of a window, and that will open a new window where you can put your tab, and you can drag it back again. And also, we noticed that people tend to use a search box and an address box in the wrong way, and I do it myself. I type in URLs in the search box or searches into the address bar. So in Google Chrome, we've combined the two so that you only have one box where you can type things into, and we call this the Omnibox. And the Omnibox is going to help you find what you need pretty fast. So if you type in stuff, it's going to give you suggestions based on your history and based on web searches. So it'll be easy for you to find what you're looking for, even though you maybe don't remember the exact address. Also, you can just type in web searches directly in that bar, and it'll go to your default search provider and perform the search there. So we've tried to make Google Chrome really easy to use. And the final part, which is where I'll try to dive it a bit deeper, is with the speed. So Google Chrome is fast. And the speed of browsers really matters, because the faster your browser gets, the better web applications developers can create. Right, so we did two things to make Google Chrome fast. The first one is that we based it on Apple's WebKit rendering engine, which is really fast. And the second thing that we did was that we built a completely new fast JavaScript engine called V8 and integrated that into Chrome. And that's what I'm going to tell you more about now, what we did in V8 to make JavaScript execution fast. Okay, so why did we even want to build a new JavaScript engine? So 2 years ago, when we started the project, the JavaScript picture was not looking very good. So browsers had really slow JavaScript implementations, and the JavaScript implementations did not scale well with respect to code size and object allocation. So if you had big applications with lots of objects allocated, you would experience pause times, and JavaScript would become slow. And sometimes they even had memory leaks when running web apps. So to us, there seemed to be a simple solution. So let's just build our own engine from scratch and try to see if we can overcome some of these problems. So the goal of V8 was to raise the performance bar for JavaScript execution. So to show that JavaScript execution can be really fast, and hopefully help evolve JavaScript engines in general to get really good JavaScript performance. Because good JavaScript performance means faster browsers, which means better web applications. So this is really important for us and should be for web developers. So here are some of the key design ideas that we used in V8 to make it really fast. The first one is something called hidden classes and hidden class transitions. So basically, this enables us to group objects based on the properties that they have. So basically, as in a class-based object-oriented language, where you know that each object has a class, we try to do the same thing in JavaScript behind the scenes. That's not true in JavaScript, that there are classes. There are no classes in JavaScript, but we introduced them behind the scenes. And the reason why we did that was that it enabled us to use a technique called inline caching, which is an optimization technique, which will make property access really fast. And I'll come back to this. The second thing that we did was we compiled directly to native code. And the third thing that we did was where we've got an efficient memory management system so that we can scale with respect to the number of objects that you have and not get big pause times when you do garbage collections. Okay, so I'll take each of these in turn. So I'll start by looking at the hidden classes and hidden class transitions and how that helps us make property access and function calls fast. So What are the challenges in implementing JavaScript? Well, the main challenge is that JavaScript is a very, very dynamic language. So objects are basically just mappings from names to values. And properties can be added and they can be removed on the fly. So that means that when you have a property access side, if you have an object O, if you have O.x, you don't know anything about O. You don't know what the object is. You don't know what its layout is because it can be anything. And it's just a map from names to values. So objects with completely different sets of properties and completely different layouts can appear at the same property access side. And not only that, in JavaScript, you have what's called the prototype chain. So each object has a prototype. And properties can also be found in this prototype chain. So you can get objects with completely different layouts. You can get objects with different prototype chains at the same site. And also you can move functions and properties between objects any way you like. So it's really dynamic. So basically you don't know much when you want to access property X of some object. You don't know anything about that object. And that makes it a bit hard to make it efficient. And here's why. So if you have a static object-oriented language, which is class-based, then you know for each object what its class is, and based on its class, you know the exact offset in the object for the value of that property. So all you have to do when you want to load a property X from an object is just fetch it out from the object at the location where you know that it is. And that's really fast. In JavaScript, as I just told you, these properties can appear anywhere. They can be on the object in different locations, and they might be in the prototype chain. So basically, you have to do a complete search. Whenever you look for a property X in the object, you have to search the object to see, do I have an X? If not, you have to go to the prototype and repeat the same thing. And that's pretty slow. So we wanted to get away from that. So we wanted to actually get some of the benefits you have when you have classes. So we wanted to try to introduce classes behind the scenes. So JavaScript, in JavaScript, you create objects based on functions. So here's a simple function. It's called point. It takes an X and a Y, and then if you call this as a constructor, it creates a new object and assigns X to the value, creates an X property, assigns it to the value passed in, creates a Y property, assigns the value passed in. So you get an object here with two properties, an X and a Y. Okay. So now let's try to see how we relate all objects that are created using this function. So we want all points to be related. We want all points to have the same class, because then we can use the class structure to do optimizations and make faster lookup. So let's look at the first thing here. I create a point called P by calling the point function as a constructor. So what I'm doing here is that I'm creating a point object that has some backing storage. It has room for some properties. And then every object that I create from the point function, I'm going to start out by giving them the hidden class C0. Okay, so this point object that has nothing in it right now has class C0. Okay, and once I've created the object and giving it the initial hidden class, you start executing the body of the function. So here I'm putting in the X value of the point. Okay, so the way I'm doing that is that I put the value 1 in the backing storage of my object. Then I create a new class, a new hidden class called C1 based on class C0, where I say that X is at offset 0. So now this object has a class that says that X is at offset 0 in my backing storage. And also, I record in the initial class C0 that if any object with this class gets an X property, that object has to change its class to class C1. Okay? So now let's do the same for Y. So we put in the value for Y in the backing storage. We create a new class C2 based on class C1, where we record that Y is at offset 1 in the backing storage. And again, we record in class C1 that if you have an object that has class C1 and you add a property called Y, you should do a hidden class transition to class C2. Okay, so now we're done creating our first point. And you see there's a bit of overhead involved here. We create hidden classes and we record hidden class transitions. But this is only something that you have to do once. Because if I create my new point now, the next point, the point Q, I'm going to do basically the same things. Because I create my point Q, which has a backing storage for holding properties. And point is created from the point function. All objects created from the point function get the class C0 as its initial hidden class. Okay? So now when I want to assign to X, I can look at the hidden class of point Q, and I can see that, oh, it has class C0, and if I add X to something that has class C0, it needs to get class C1 afterwards. So all I have to do is put the value 3 in the backing storage and change the hidden class pointer. And similarly for the Y. Okay, so now you see I've created 2 points, and they share the same class. So in this way, we group objects that have the same properties using hidden classes. And now based on this hidden class, I know where my X and Y are. I know the offset in the backing storage of X and Y for points. Okay, so having introduced these hidden classes, we can actually revisit the statement that JavaScript is really, really dynamic and say, how dynamic is JavaScript at runtime? And it turns out that roughly 90% of all access sites only see objects that have one hidden class. And this basically makes sense, because if you write well-structured object-oriented programs, you would expect that you that your objects have some sort of meaning, and that they flow through particular parts of your program that is written to handle these types of objects. And then there's maybe 10% or something like that that's really generic and just operates on any kind of object. But most of your code will probably operate on one kind of object. So roughly 90% of all access sites only see objects with one hidden class. So that means that JavaScript is not really as dynamic as runtime as you might think. And that means that we can use class-based object-oriented optimization techniques to make property access fast. And the way we do that is that we generate code on the fly. So whenever there's a property access or a function call, we create what's called an inline cache stub, which is a piece of code. And those stubs can be in one of 4 states. So it starts out being uninitialized. And uninitialized means there's a property lookup here, and I haven't seen any objects yet. So I haven't seen any hidden classes yet. Then there's another one called pre-monomorphic. That's not that important. It basically means I have seen a hidden class, but I'm not willing to commit yet. And then there's the third one. And the third one is the really important one. And that's the one that's going to be hit by 90% of all property accesses. And that's the one called monomorphic. And in a monomorphic state, your stub has only seen one hidden class. So it has only seen objects with one hidden class. And based on that one hidden class, it knows the offset to the values inside of the object. So it will be just as fast as for your static class-based object-oriented languages. It can just pull out the value directly. And then if that fails, so if you actually happen to see more than one hidden class at one property access site, you'll go to a fourth state called megamorphic, many forms, meaning that you've seen more than one hidden class, and then you have to actually do the lookup. So here's an actual inline cache stub for loading a property. And this is x86 assembly. And as you can see, it's really short, right? So I just wanted to show you this slide to show you that this is really efficient. You don't have to do much to load a property if you're in the monomorphic state where you have only seen one hidden class. So let me try to walk you through this. So what we need to do here is we need to load the object from the stack. That's the first line. And then the next 2 lines is just an extra check. So all of our pointers are tagged, which means that we have a way of figuring out if something is an integer or if it's actually a pointer to an object. So this next check checks that we actually have an object. If we don't have an object, we jump to the bottom line, which jumps directly into the runtime system, and it will rewrite this stub and say, okay, I've seen something that was not an object of this type. Okay, so load the receiver, check that it's not an integer, check that it has the type, the hidden class that you expect. So the value out here on the right, that's the pointer pointing to the map that you expect to see, to the map, to the hidden class that you saw the last time that you got here. Okay, so that's the pointer to the hidden class you saw the last time you were here. And then we just take out the hidden class of this object and check if that's the same. If it is, we jump in here, we just fall through to here, and we load the backing storage, and we load the value directly from an offset inside the backing storage. So basically, all you have to do is load the receiver, check that it's an object, check that it has the right hidden class, and then just load the property. So that's the usual case. That's what you usually do for a property access, and it's just a few assembly instructions. Okay, so that was for the hidden classes. So we chose in V8 to compile directly to native code. So we don't have any bytecodes, and we don't have an interpreter. And the reason for this is that basically there's no reason to have bytecode or an interpreter, because in JavaScript you transmit the actual source code over the internet, and there's no defined bytecode format. And we need to keep the JavaScript source code around anyway, because you can do toString on all of your functions and get the actual source code of the functions. So basically, we need the source code anyway, so why not just take the source code as our first representation and compile it directly to native code? So that's what we're doing. That doesn't mean that we compile everything when we load it. We just record that there's a function, and that function has this source code. And then the first time you actually want to use that function, we compile it into native code. And our compiler is pretty simple. It just passes the source code into syntax trees, and then we have a simple one-pass code generator. And it doesn't really optimize much right now. And we have code generators both for x86 and for ARM. Okay, so now on to memory management. So in V8, we wanted fast object allocation. We wanted it to be really fast to create new objects. And we also wanted a scalable object heap where you could get small garbage collection pauses. So we do not want programs to degrade just because you allocate a lot of objects. And we do not want people to experience big pause times when they're using their applications because JavaScript is garbage collecting, removing objects that are no longer used. So in order to do that, V8 uses what's called a generational garbage collector. So this is what the object heap looks like. So we have 2 generations, a young generation and an old generation. And the young generation is where we put all of our newly allocated objects. And we do garbage collections really frequently in the young generation. And the idea behind this is that in object-oriented programs, most objects that you create die really young. So a lot of objects are basically just temporary. So you create a lot of objects, and they're basically dead immediately. So we put them in new space, and we garbage collect that frequently. And often that's enough to keep space available. But also we have an old generation. So for objects that do not die young, we want to be able to move them somewhere else so we don't have to look at them at each garbage collection. Okay, so the old generation, we do not garbage collect that frequently. We only garbage collect it when it's needed. So if objects survive a couple of garbage collections in the young generation, we move them to the old generation because then we don't have to look at them when we do new space garbage collections. Okay, and the old generation has a number of different spaces with different properties. I'm not sure it makes sense for me to go through them. Some of it has to do with which spaces need to have executable bits set. Some of it is about object sizes. We have a special space for really large objects that we don't really want to move around because that just takes too much time when they're that big. Yeah, I think that's all I'll say about that. So the important thing here is that we have more generations. So we can garbage collect frequently in the young generation, and we can move objects that survived a couple of garbage collections to the old generation, so we don't have to worry about them when we do young space generations. Okay, so we have 3 different types of garbage collection. So the first one is the scavenge collection. And the scavenge collection only looks at the young generation. So this is what we do all the time. And we use what's called a copying collector. And what a copying collector allows us to do is to have single pointer allocation. So that means that whenever you want to allocate an object, all V8 has to do is just move a pointer, and then you have some space that you can use. So object allocation is really fast. It's just a matter of incrementing a pointer. Right? A copying collector has really small pause times, so an average of 1 to 2 milliseconds to collect the young space. And the pause time is bounded by the amount of live data in the young generation. Okay, so you see 1 to 2 milliseconds is really fast. And since this is what we do most of the time when we do garbage collection, you won't really see garbage collection pauses. So sometimes we do have to clean up the old generation. And for that, we use a mark sweep collection. And that looks at all spaces. It looks at both the young generation and the old generation. And we use both single pointer allocation and free list allocation. So there's a combination there. And for a mark sweep collection, the pause time is bound by the size of the heap. And remember, this is the entire heap. This is both young and old generation. So the typical pause times that you'll experience when we do full collections is 30 to 50 milliseconds. And sometimes we end up having some fragmentation in the heap. And if we detect that we have fragmentation in the heap, we do a mark sweep compact collection, which does a mark sweep collection, but it also compacts everything to remove the fragmentation. And the typical pause time for that is like 50 to 150 milliseconds. Okay, so here's another interesting thing about V8. So in JavaScript, you have some built-in functions like string.prototype.join or array.prototype.join, sorry, string.prototype.replace. So you have all of these like split and search and match and whatnot. And all of these library functions in V8 are implemented in JavaScript. So we have not written them in C++ inside of the virtual machine, but we've implemented them in JavaScript itself. So why did we do that? Well, the benefit of implementing this in JavaScript instead of inside of the engine is that you have less code in the engine. It keeps the core engine cleaner. Also, the JavaScript code is really easy to change and extend without having to basically recompile everything. And also, it has the nice benefit that if we improve our compiler, the speed of our libraries will increase too. Because since we wrote these libraries in JavaScript code, that code is compiled by our compiler. So if we improve our compiler, we're going to improve the speed of our libraries too. So there is one drawback, though, to taking this approach. And that drawback is that since these libraries are really needed, you need to load them when you start up your JavaScript engine. So since they're written in JavaScript, to load them means that you have to take the text, you have to parse it into syntax trees, and you have to generate code for them. And that's actually a bit of work at startup time. So it gave us a startup time of roughly 30 milliseconds to start up. And that's a bit much. Luckily, there's a solution to that problem. So what V8 does is it allows you to save the state of the initial heap into a binary thing, which is called a snapshot. And then when you start V8, instead of actually having to parse and compile all of your JavaScript code for the libraries, we already have done that. And the native code is in a heap, and we've dumped that heap to a binary file, or to a binary image that's embedded inside of V8. So when we start up V8, all we have to do is just slurp in that binary data and start, because we have all the code there. So with snapshotting, the startup time is reduced to 4 to 8 milliseconds. So that's a bit of cool technology to make it feasible for us to actually have the JavaScript library implemented in JavaScript itself. Okay, so with V8, we released a number of benchmarks. I think it was 5. And it's roughly 11,000 lines of JavaScript code. And this code was not written by us. These are examples of object-oriented code, well-factored object-oriented code. And it's the kind of code that V8 shines on, and it's the kind of code that we think people should write, well-factored object-oriented code. And I think that's all I wanted to say about V8 for now. So you can go to code.google.com/p/v8. That's the location of the open source project. That's V8. So V8 is fully open source. You can see all of the source code. You can see all of our development online. We're doing all of our development live, and you can see all of our code reviews and all of our code. So please go there if you're interested, and I'll be happy to